mass by the ratio of the mass and the distance. So it's all algebra. And let's go to a few more properties. Once again, here's the metric. And obviously something interesting happens when the radius you're at is equal to 2m or larger, because then this term becomes 1. And we call that the horizon. That's a common term in studying black holes. Something important happens there. So for this radius, when you get far enough from a mass, this space-time interval exceeds the time interval by this ratio. And this is called a redshift. That is, the farther you go from the mass, the slower the clocks go. A lot of this refers back to what many of you saw when you were studying special relativity. So Einstein's very general approach produces the same results as special relativity in a much more elegant way and applies everywhere except where the radius is 0. That is, this formulation applies for black holes right down through the horizon, all the way down to the point where the radius is exactly 0. So even if you're being spaghettified, you could take great comfort in the fact that this calculation will tell you how time evolves for you. So now let's spend a half an hour kind of generated the ground rules for what we're doing. So how does GPS work? Well, there's a whole bunch of satellites, 24 I think, in different planes and so forth, and they're radiating signals, radio signals, and the radio signals are encoded with time based on very high quality clocks that the satellites carry. So they use atomic clocks and propagate those signals to the little receiver that Dennis just bought. And as long as you can see four, so you have to see 4 satellites. 3 of them essentially produce intersecting spheres, and your little pocket device calculates where you are. The 4th does a calibration for the clock rates. So, as I said, tied to these clocks are timing signals, and that's a trivial way to present what GPS does. It's much more complicated than that. But the point is that we're going to use the equations we just looked at, the Schwarzschild metric, to look at what we have to do to the clock rates to make them work, because the clocks are out in space, away from a mass, so that little term r is not the same r that we experience. So the clocks are running different rates. If you bring an atomic clock from one of those satellites down to Earth, it will run at the Earth rate. If you put it in a satellite and send it out to its orbit, it runs at a different rate. Even though nothing's changed, when we detect the signal, we see different clock rate because of the gravitational influence of Earth. So here's the metric again. And imagine that we're on the surface of the Earth. We can do a little arithmetic and calculate the rate of the clock progression as a function of how far we are above the surface of Earth. And that altitude is defined by r, the radius at which we are doing the calculation. So at every altitude, this formula applies. And here's tau, the time-like metric, and it will change depending on where you are. The mass of Earth, of course, doesn't change, but the radius from Earth changes. So now, this is the velocity, by the way, right? Do a little, if you've seen this before, it makes sense. If you haven't seen it before, it might not. But here's the radius squared and the angular rate of the object. So if you imagine it's a satellite going around the Earth, this is the angular rate, and this is the distance, so that's actually a measure of the velocity. So here's how the clock rate depends on your radius. Okay? So now what we can do is we can say, let's establish 2 different shells on which we are going to do this calculation. One of them is at the satellite. So here's the clock rate at the satellite, And on the surface of the Earth, we have a different rate, but they both use this formula. So we can take the ratio of these, and you get this, and notice here is the velocity of the satellite, the altitude, here's the velocity of your observing point on the Earth, and here's your radius from the center of the Earth. And this is squared, so we have to take a square root, so we have this formula here. So here's our second page of analysis of GPS. Now let's take a simple case first where nobody's moving, where the Earth isn't rotating and the satellite is just hovering out there. So things get simpler. We have this equation from the prior page, except that the velocity terms are going to be 0, these two terms. So remember, we already did an approximation thing where we expanded a square root this way. That is, if you add some small number to 1 and take its square root, it's approximately equal to 1 plus a half of that addition, and so forth. Now, because we've already agreed that the mass of Earth in these units is very, very tiny relative to the radius of the Earth, it's less than a centimeter in the coordinate system we use, that's a very tiny number. So this approximation applies, and we get this. Here's the ratio of the clocks. Remember that square root from the previous page, and now we can use this approximation and this approximation. We get this, and we can multiply it out. And this is going to be even smaller because it depends on the mass of Earth squared, which is a very tiny number. So this is going to go away. We don't even need that. So here's the relative rate of a satellite clock designed and built on the Earth, identical to a clock that's on the Earth that didn't take the trip into space. And the difference between the rates of these two clocks, just from general relativity effects, is this. It's 1 minus the mass of the Earth divided by the altitude of the satellite plus the mass of the Earth divided by the radius of the Earth. So once again, we're able to do some great things here with just simple algebra and a few approximations. Now we're still in the zero velocity case. So let's put some numbers in. Here's the mass of the Earth in the units of distance, 0.4 centimeters. Radius, the altitude of a GPS satellite turns out to be 26 million meters. Here's once again the mass of Earth in distance units, and the radius of the Earth is 6,378 kilometers. And we do some arithmetic, and what we find is the clock differences, that is the relative rate of a satellite clock and an Earth clock, is equal to 1 minus some number times 10 to the minus 10th. So there's a little tiny difference between the clocks in space and the clock on Earth, even if they were built identically and use the same atomic material to produce the clocking, the ticking that goes on in the clock. So, what does this mean? Well, in one day, which is 86,000 seconds, the satellite clock will advance 86,000 seconds minus 4.5 times 10 to the minus 5 seconds. So it's about a microsecond difference. Well, that sounds pretty small. Why would we care about that? Well, it matters because the calculation that Dennis's GPS receiver does depends on the relative arrival rates of the timing signals, and light goes about a foot per nanosecond. So this correction, 5 times 10 to the minus 5, produces an error of about 10 miles in the estimation of where you are. You'd be uncertain by 10 miles, which is terrible, but not what we're hoping for. Particularly if you have a a GPS guided bomb system and you want it to land not on the Chinese embassy. Or if you want, many of you might have noticed the landings you're getting on commercial airliners these days are pretty good. And most of them are GPS guided, unless the pilot wants to practice. And then it's not so good. But the GPS-guided landings are really, really good, and they wouldn't be good if you're off by 10 miles. That could be a problem. Incidentally, notice this is a blue shift. That is the light coming to the radio signals coming to Earth from the satellites. Is the clock up there is running fewer ticks, and it appears to be running faster when it arrives here because this sign is negative.
And did they know this when they designed and launched
I am
the first
so
generation?
glad you asked that. I am so, hold that question. I can pay, I'll give you your money later. Okay, so in a minute we'll address that. So let's now, remember that calculation, let me go back for a second. It's a correction of about 5 times 10 to the minus 5 seconds with no motion. We did that problem first, so it's a little simpler to deal with. So now let's do the a little more complicated problem if people are moving. And we already know from the twin paradox that moving things age slower. Remember early in this lecture we talked about that. So let's do the calculation if we're going to allow the observer on the surface of the Earth, he's moving because the Earth's rotating, and the satellite's moving in its orbit. So we're going to add those calculations. So first of all, here's the velocity of a point on the surface of the Earth, some hundreds of meters per second, and the satellite in an orbit of 26 million meters is going almost 4 kilometers per second. So we're going to convert these to relative to the speed of light. They're little numbers, but let's jump to the next page. So now we're going to compute the effect of the motion of Earth and the satellite. So here we are, once again, this is what we derived from the Schwarzschild metric. Remember, we had to take a square root, and then we did an approximation, but this time we're going to keep the velocity of the satellite and the Earth in the calculation. So it looks like this. A little more complicated, and if we multiply it out, it looks like this. This is the relative rate, the satellite clock and the Earth clock, and we multiply it out and throw away the terms that aren't insignificant, and so we get a little different version. Here's what we had before. When we had no motion, we had this term and this term. And now we've got this velocity term and the Earth term. And the interesting thing is, here's the influence of the velocity of you're standing on Earth and it's rotating, but the velocity of the satellite is divided by a factor of 2. It's kind of interesting. It just comes out that way. And so we can put some numbers in now. We already calculated the velocities. And so here's our relative clock rate, and it's a bunch of numbers, blah, blah, blah. And we do the arithmetic, and we get a correction of 4.4 times 10 to the minus 10 instead of 5 times 10 to the minus 10. A little tiny change. So the shift is not 50,000 feet per day. It turns out to be 38,000 feet per day. So it's about 8 miles, not 10 miles. But it's important because we want to get to within 10 feet. So now this is where your question is answered. Before a GPS clock is launched, it is adjusted to accommodate the clock rate we just calculated. That is, they can do a synthesis thing and they can make a signal that's conveyed on the radio, that time, progress slower than it would otherwise. And it turned out, before the first satellite was launched in 1977, it was recognized that the correction was needed, but there were big arguments about whether it should be added or subtracted. And prominent people with a background in general relativity had big arguments. In fact, a guy named Carroll Alley, who was prominent in the development of GPS, had to convince the management of the program at the Navy that you didn't have to do this correction twice. They thought that if you have a satellite in space, you would have a general relativistic effect, which they weren't sure of the sign. It was either a blue or a red shift, and that the clock on the ground would also be affected by the mass of Earth. So you had to make they thought you had to make the correction twice. Well, it turns out you don't. You make the correction once, because the two observers, if you were traveling on the satellite, you would see the clock running at the same rate it ran on Earth. If you traveled with it to the satellite, the observer on Earth would have an identical clock on the Earth, and it's run at the same rate as the one that took off, but now they're running at different rates. So people got very confused. In any case, so what they did in the first satellites is they built in a synthesizer that could go either positive or negative. They had the atomic clock, which has an incredibly small drift rate, but then they put a synthesizer there so because they just didn't know which way this effect would go. And so they were able to span a large enough range in the clock frequency to encompass all the possibilities, and then they turned the system on and actually